reality. Welcome to reality. Welcome to reality. Welcome to reality. Reality. Welcome to reality. Welcome to reality. Welcome to reality.
Hello and welcome to reality. We're your hosts, TechTranslate, and myself, NOPEGENX, tackle flat Earth misinformation spreading through social media. I generally keep an eye on YouTube and Facebook, while TechTranslate is focused on X. And each episode, we'll be looking at one subject and going through its reality with you. Now, I say one subject because technically this is part 2 of the same subject.
Yeah. Last time it was gravity, totally misunderstood, and we approached it from the Newtonian and basically the misunderstanding of flat earthers, its density and buoyancy. We showed basically why this is nonsense, and we were explaining also the oddities which gravity has, and on the Newtonian way. And we mentioned already there's also another theory, and this is what is very often criticized by conspiracy theorists. Why do you have another theory? Why do you change in between them? Or you have one, and then if you see something else, you drop one. So we will also talk about what is a theory and why. What is the difference to a theory which we said casually? No,
yeah, and it does need to, like, obviously, I'm sure other channels have already specified it, but obviously it's part of our reality and it's something that we need to deal with. It's good to see some people coming in. Let's have a little say hello to some people. Mr. P. Bowles, thank you very much for showing up. Really good to see you here. Here to learn. Well, this is the right place. I mean, I have German engineering on my side. You know, it is the best in the world. So we will be able to do that. Hi, Nightwolf. Good to see you. Thanks very much for showing up. And I hope everyone can settle in because we're going to be tackling Einstein's relativity.
Oh, Jesus.
It's, yeah.
What?
Tech's kind of put himself in it this time because it was his idea to do gravity last week, but obviously Newtonian works on Earth, but when you start looking at light speed, you need a little bit more added to it, and it gets very, very complicated. So I guess without further ado, I will ask Tech to bring up his slides because I don't have them on the deck here, and we can present them for you. But anyone got any questions as we're going along, please put it in chat, and obviously we'll stop and try and give you the reality answer to these things.
My monitor, I hope.
Yep. I will just
see it.
Get some. Take that one off. Thanks, Niles.
So,
and here we go.
Oh man, this is the wrong one.
That's the wrong one already. See, it's confusing.
Okay. We tested it 1,000 times, but we got it wrong. It's computer.
It's like doing science. You know, you got it's repeatable, and sometimes it goes wrong.
Yeah, sometimes not. So this falsifies the theory. Yeah, today.
Which one do we want?
Yeah, we called it Gravity Part 2 Misunderstood. And one disclaimer in front. I'm an engineer. I'm not a physicist. I'm not a mathematician. Normally it works this way. The mathematicians, they make our tools, mathematical models. The physicists use them, make scientific theories out of it. And as an engineer, we take only this one which we need, now, because what we build has to be it has to be safe. it has to be, it has to work. It's an honest job. Yeah, it has to work, and it has to be cheap. Now, this is basically our constraints, and this is how we work. And so, in my entire engineering career, so also in university, we were taught only Newtonian. Yeah, and I
That makes
remember
sense.
only 2 times in physics lecture where we had an exercise where we had also to do something with relativity. No, and so basically, I'm not going now in deep mathematically. I will basically tell what is happening and basically explain the framework around general relativity or relativity in general. Yeah.
Okay, well,
Okay.
before we do that, we'll just say, Nikoti, thanks very much for turning up. Yep, don't worry about moderating. And we initially kind of wondered whether we would actually get flat earthers trying to argue reality, but it turns out they're a little bit scared of our kind of reality, and they don't tend to show up. So don't worry about moderating. I'll keep an eye on that for you there, my friend. But good to see you, and thanks very much for showing up. And hopefully we can get on with some reality. Let's put this on the stage for you. There you go. As usual, we kind of duck out. We let the man himself do his thing. Now, he is under strict orders not to waffle on too fast, but I kind of like, in fairness, though, you can change the speed when you're rewatching it. So don't give him too, he gets excited and he gets into it.
This time not to run through the subjects, because
if there's still stuff to go,
yeah.
If there's things to do at the end, we'll probably just run it as a second stream, so it's not a big deal either way. But yeah, let's crack on, and hopefully everyone will stick around and enjoy the show. Thanks very much. I will duck down, and what should we do? That one? No, let's make it like that.
Yeah, right. And here on the first slide, or basically on the cover, we have, I think most of you know this is from the movie Interstellar, a black hole. Yeah. And it looks a little bit weird. Now we have here something black here, we have something here in front and something over it, which looks distorted, and something underneath. And first of all, this is basically, until the movie Interstellar, how we saw black holes in magazines and so on. It was always an accretion disk where the matter is basically like in a sink, spirals down to something which is black, and a jet is coming out here. And it looked like this. This is for a long time. This was how we
classic.
Yeah, and also in scientific magazines, it was always depicted like this. And so basically the question is, why or how did we come from this one to this one? And I spoiled it already. It is basically from the movie Interstellar. There was the first time a black hole realistically displayed for a broader audience. No?
And very different to the ones you see on Star Trek or Star Wars.
Because I think they did not want to explain why it looked like this, and it is a little bit counterintuitive. And the interesting thing is, for Interstellar, they worked close together with NASA scientists, and basically it was the first moving simulation based on general relativity formulas of a black hole. Now, so to have it in real time, nearly in real time, basically moving. And so this was a very interesting thing also for NASA to get this visualization, because this was not cheap to do. This is really, you need much more CPU power than when you render this.
The processing power of making a circle is a little bit different to making a moving black hole in its actual relative image. Yeah.
And I think the other reason is black holes, the closest we came were like this. This is one galaxy. It's a very big one. It is, And basically, you see a little bit, and this was basically how the strongest Earth-related telescope could see it. And we see here also the plasma jet is coming out. Basically, the matter is compressed here, and a part of the matter reacts violently and goes here out nearly with light speed. So relativistic jet you have here. And but we still don't see the black hole. And the closest we came originally with Hubble. Now, this is the same one. And basically here we see something which resembles an accretion disk, but it is much far out of it. Now,
that looks more like the sci-fi that we know, doesn't it?
Yeah, and I think this was the reason why in science fiction and everywhere they showed it like this. No? And the interesting thing is, this was the first ever realistic visualization of a close-up of a black hole. It was illustrated by Jean-Pierre Luminet. He was a physicist, astrophysicist, and it was in 1979. Yeah, so it is nothing new. It's nothing new. It was known how it looks like, and he used at this time an IBM mainframe computer, one of these really big machines, and compared to our PCs today, they were very slow.
Size of my spare room, that thing.
Yeah. And he calculated basically on a few major points where they should be, and then he illustrated the rest with his artistic skill, no? And how, according to the theory, it should look like. No? And here you
kind of guessed it, but he used the actual theory of what it should look like to fill in the blanks, and he did a pretty good job. That's pretty close to reality, isn't it?
It really looks like an Interstellar, and it's a pity that it was not explained, and we saw always these disc-shaped objects. But regarding disc-shaped objects, this is basically how black hole were illustrated. Yeah, and it was basically according Newtonian. Yeah, we are looking from this side. We have here the accretion disk a little bit tilted. This is the event horizon. We'll say later what it is. Basically, nothing can escape when it passes the event horizon, even not light. And if you look from this side, it looks like this. This is after Newtonian.
It's more like a hat, isn't it?
Yeah, like a hat. And this is basically how we saw it in science fiction and also in scientific magazines. But relativistic or looking with general relativity, I think everybody heard bending of space-time, things like this. It is crazy stuff. And yes, it bends space-time. And according to general relativity, the space-time is bent next to the black hole. And basically, we look not up like here into the distance. Our line of sight is basically here curved down. Okay, normally light is emitted and goes this way, but I think it is a good visualization to show it this way. So basically, this is where we look on. No? And our brain, and also it's the same on photo, when something comes from this direction, we assume it must be in this direction. And so it looks for us if this one is up here. And here the same, space-time is bent, it goes here, and we see it like this. And then it's basically this result what we get. This one, this thing here is basically this, we're looking on this, and this beneath the disk is basically this. So basically this is the same thing, upper side, lower side. And this is basically...
And the bending of space-time is to do with like the actual light particles traveling, isn't it, against that black hole and its gravity. So, and we'll look at that in a lot more detail. So don't think that we're just going to say this is it, because there's a lot more to it.
Okay. This is basically the teaser, but I think it's quite interesting to understand why it looked so weird, because in the movie they did not explain it. No? And the other thing is, is this a mirage? This is a question. Yeah, does it only look like mirages like Fata Morgana? You go there and there's nothing. Yeah.
Yeah.
The question is this the same? And no, space itself is bent. This is a straight line through space. Yeah, it's not possible to draw it otherwise, but it is a straight line. Space itself is bent. So when you go in a straight line to this one, you end up here. And if you go straight in this way, you end up here. Yeah, so basically here. And this is really weird. No? And why these are the
it's why I struggle with it, you know. And I'll be honest, Newtonian stuff makes perfect sense. I fully understand it. You know, it's a mass attracting mass, it's a gravitational acceleration, and all those kind of things make perfect sense. They work, they're tested, you know, and they're proven, and they haven't ever been debunked. When you get out into space and you're dealing with much faster speeds, you know, the speeds of light and gravity being affected by light is where it all gets a little bit kind of tricky. And I think this is where most people actually are like me, where they fall over and kind of can't compare the two ideas.
Yeah, this is true. Yeah, this is counterintuitive. Now this is
yeah.
Okay, and
but don't worry, we've got you. We'll explain it.
We talked already about general relativity, the bending of space-time, but maybe you heard that there are two steps, basically: special relativity and general relativity. Special relativity was the first thing which Einstein basically made the mathematical model, and this is for non-accelerated reference frames. So basically, when you're not accelerated, you're moving at a constant speed. This is basically for what special relativity is. And it describes phenomena like time dilation and length contraction at high velocities. We go into this later on. And the next step, which was much more complicated, is also to include accelerated reference frames and also very strong gravitational fields. No? And basically, it models the gravity as the curvature of space-time. It does not see gravity as a force anymore. It's a feature of space-time. And we are not looking, maybe you know this formula, the most famous formula. So energy is mass multiplied by the speed of light squared. We are not going into this one too much, but when I write general relativity, I thought I have to mention this. What it shows is it is the equivalent principle of energy and mass. So basically, you can convert every piece of mass into energy, and light speed is very fast. So also 1 kilo or a few grams is more than a nuclear bomb of energy which is inside it. No? But fortunately,
pretty scary stuff.
Yeah, this was also what is behind nuclear bombs. You have a very small active warhead, and this uranium or plutonium, it is possible to release a fraction of this, according to this formula. And this is basically why such a small thing can be so devastating. For example, I heard these big nuclear submarines of the Americans. They said, we have an orange big part of plutonium here in our reactor, and we can drive 20 years with this. This is basically
just one little piece.
Yeah, and like an orange in the size. And this is
think how far I'd get in my car if I could run it off a nuclear reactor, eh?
Yeah. So, okay.
Not sure it's very safe, but and it'd be a rather large car in order to contain it. But
there were plans for nuclear cars in the United States. General Motors made not a prototype but a concept. But of course, this never was realized. No,
I think when you get home and all your shopping's been radiated and you can't eat it, not very helpful.
Yeah, okay. Now, we had this slide also the last time, and it is basically the phenomenon of gravity. The apple falls down. We see it. We are used to it. And we normally think something different. We would never expect it would fly upwards or sideways. And why we do expect this? Because we are used to it. We are used to it falling. We never saw it in a different way. So it is for us nothing special. So the observed phenomenon is the apple falls down.
Yep.
And in Newtonian, a force is pulling it down. And when you think about this, this is wild. Yeah, like magic, nobody touches it, no string, an invisible force. You cannot shield it. It attracts everything. Now, when you look
Yeah,
at from
it doesn't
this
matter
side,
whether it's in a vacuum or anywhere, it
yeah,
still happens, doesn't it? So
and this is really when you look at this thing which we have all day from this side, you think, why is this? And yeah, we come to this later on. And this is basically according general relativity. The apple does not
it's
fall. For the observer, we are standing here. For us, it would be the same result. The apple falls. No? But according according general relativity, basically the floor moves up. Makes
the
first of all
earth
no
moves up.
sense. Why should we do this? Yeah, it would look for us the same, but why do something insane? No. And basically, one thing why we can look at this way is the equivalent principle, which Einstein basically claimed was that acceleration and gravity is the same. Yeah, when you're
Yeah.
standing here on Earth in this chamber and you drop a ball, it falls. And we have the gravitational acceleration, which is 9.181 meter per second
1.81 meters
squared.
per second squared. Yeah.
And if you are in a
I'll
rocket,
speak quickly then. Do we get
yeah,
quick, slow everything down, repeat it? Yeah.
okay. And when we are in a rocket which accelerates with the same rate, we would experience the same. Now, this one is accelerating, we drop it, and if we cannot see outside, for us it's exactly the same like for him.
Yeah, and that's the thing of like why Newtonian gravity works for us in our reference frame, isn't it?
Yeah,
And
So,
that's why it works every time for us in our reference frame on Earth. And it's only when you go outside of Earth that the Einstein's theory of everything moving up is kind of taken more into consideration.
exactly. And the same is basically, sorry, I copied this from somewhere else.
Let's hope we don't get copyright strike for it.
when you're in an elevator, yeah, and the elevator is falling down, the chain snapped, yeah, you would experience weightlessness when you fall. No? But of course, the fun would be very short. You will slam into the ground.
Yeah, it's a rather short trip. And
yeah.
I mean,
For a moment, you
can
feel like an astronaut. Yeah? And this is also equivalent here when you're far away from any gravity source or when you're in orbit, you're also basically in free fall. So every time we feel no force on us, we are basically falling according general relativity. Yeah? And here we free falling towards the Earth. And here we are floating basically, or in an orbit. We come to this later, why this is also a kind of free fall.
Yes.
You saw maybe these visualizations of bending of space-time. I was never happy with this, and I think this is more. I think it raises more question than it answers. Now you have here something. It looks like a funnel, and here you have here something, and this is two-dimensional representation of bent space-time. But
it's a very simplified version, isn't it?
Yeah,
but
and
it's the one that we're all familiar with, unfortunately.
Yeah, but the better one is this one. This is how it would look like dimensional.
Dimensions, yeah. A
So
three-dimensional image, yeah.
From all sides, the space is curved. Basically, these are straight lines. Now, if you would, we see it now from outside as if we could see that it is bent, but if you are traveling along this one, it is one direction. And the other thing is, on this line, if you stay on this line, you're in one reference frame. No, and I took this from here. I can recommend this YouTube channel, Science Click English. No? And this is when we put in the fourth dimension. And as long as you are in one of these lines, you are not moving relatively to space. So my red dot is not moving right now. Yeah, it is not moving relatively to space. Basically, Earth or the mass is curving space-time. And this is basically what we mean when we say curvature of space-time, not the other thing. This is a two-dimensional representation, but with the computing power of today, we can simulate it quite nice. And this is basically how space falls down. And here now we have an apple. It stays exactly at the same point on the line, so it falls, but it is not moving relatively to the space. Now it falls on Earth. It cannot fall further. Yeah, Earth stops it from falling. So basically, what does Earth do? Relatively to space, it accelerates upwards. Yeah, it keeps the same size, but it space is falling down on it, so it's accelerated upwards. A satellite is moving basically in a straight line, but because the space is falling towards the Earth, it keeps it in orbit, and this is a free fall. Yeah, constant
that's
speed.
the same with the
So
moon and the
falling
us around the
towards
sun.
Yeah, you're falling towards this one, but you are so fast that you never hit it, basically. No?
Yeah, because you're the actual momentum that you got. Just to clarify it for everyone, the momentum of you in that orbit is enough to prevent you from being pulled in towards the bending of space-time, isn't it?
Exactly. And now, okay, what we have now, we have Newtonian. Newtonian was quite simple. We have gravity as a force.
I'm okay with Newtonian.
Yeah. Me too. We scrap the rest. Okay, stream finished. So
yeah, that's it. We'll just leave Einstein to himself, and everyone just.
So basically, according to the theory of Newtonian, masses attract masses for reason unknown. They do it, yeah. And so basically, we would feel a force downwards. In reality, we have also a mass. We attract also the Earth, but the Earth is much bigger. So basically, we can keep it like this one. Now and what we feel is the inertial force. Basically, when you fall on the ground, it feels as somebody is slamming into your face. This is basically this one, the inertial force, and the gravity pulls you down. And this is basically the main formulas. These two formulas are basically the main formulas of Newtonian gravity. This is the gravitational acceleration multiplied by the mass is the gravitational force. And between two masses, you put here's this gravitational constant. This is the distance between them. You have the force which both interact on each other. In general relativity, we saw already, we are accelerated upwards. Yeah, but
Six-axis stage is asking us to remember that 2D and 3D, etc., are tools for measuring reality, not reality itself. And I would agree with that. Obviously, like we're kind of welcoming you to reality, or I'm sure you're already here, but yeah, these are tools to illustrate the measuring, as it were. But yeah, I mean, it does make a good point. But yeah, sorry.
No problem. And yeah, so basically, this is what we saw in the movie, in the short clip. Now, the ground is accelerating upwards, and what we feel is the inertial force. For us, it feels as if the inertial force is pulling us down, but in reality, reality in quotation marks, we are moving upwards. Yeah, and you see the arrows, the color of the arrows are, or the arrows with the same color point in the different direction. You know? And you see this one with two formulas you can describe gravitational field. Basically, you can calculate the gravitational force. When we go to this one, this looks quite ugly, and I tell you, I don't understand.
Looks rather confusing.
There's a lot of I here this gravitational constant is the same one with we see here. C is light speed by the power of 4, and is for some reason p and 8. So this looks basically like a spherical formula to me, and this is the simplification. And
yeah, that's the simple version of the one above it. Everyone, you know,
you have to know these letters here. They include something always like a very big formula is behind these ones. Now this is basically a brief thing, and this is for just one gravity source, no, and this is the space element basically, no, and this is basically yeah. And if we look on flat space time, so no mass, then we have this, and this we see this looks a little bit like Pythagoras. No? So you have s squared is x squared with y squared. No? And when we have a gravity next to it, it becomes this ugly thing. And now we will Occam's razor. I'm sure you're familiar with this. Occam's razor basically says, if you have two explanations for one and the same thing, use the simpler one. And I think we all agree that this is the simpler one. Huh?
I'm on that one.
Yeah, but why are we doing this here? Now, it makes, first of all, no sense. No? And one of the reasons was already in 1800, Newtonian was very well understood, and it was possible to calculate very, very precisely. I was really surprised, but you could really measure in detail and verify Newton's a law of Newton's Newtonian gravity, and all planets exactly behaved like this. Yeah, and it was also because in disturbances, and these planets are really big. Now, this is not to size, by the way. No, they are really big, and because they saw a little deviation, they noticed there must be another planet. No? And then they calculated also basically where it has to be, and then they discovered it. And it worked already the same way with Neptune, no? Because in disturbances of these planets, they realized there must be another one. They calculated where to look. They found this one. No, and this is really amazing.
That was just maths, isn't it?
Yeah, that's really amazing. That it was already then that I calculate possible to calculate, but they struggled with Mercury. Mercury was behaving a little bit different.
The unruly child of the lot.
Yeah. And they took in consideration all other planets, but it was still a teeny bit out of sync, which cannot be explained. No? And there were theories then that there might be also another inner planet. As I said, these planets were discovered because there were disturbances in this orbit, so they thought maybe it's the same. Maybe we have very close to the sun one, or on the opposite side of the sun, which we can never see. Or in the sun, there is something odd gravity field, which explains this. And here we see basically nearly perfect circles. Okay, no, and in reality, these are ellipses. And they have a very close point to it and a far away point to it. No? And basically this is Mercury alone. And basically this would be one ellipse. It's exaggerated. Now, normally it is not such a big ellipse, but exaggerated, it looks like this. And the nearest point, according to Newtonian, it would never shift. But in consideration of the other planets, it would shift. Yeah. And then they found out in 1859 here, Urbain Le Verrier's observations.
Good pronunciation.
Yeah, I had French a little bit in school, so I try my best. The speed, this perihelion is called the closest point in the ellipse to the sun, was moving a little bit faster than expected. No? And it was not explainable with Newtonian mechanics. No? As I said, they came up with wild theories, but they really had no explanations. And also at this time, there were the first thoughts that maybe a new theory is needed, which predicts also the new observation. No?
Yeah, and that's what science does, isn't it? Science doesn't just throw out the old theory and replace it, because the old theory will still work. Newtonian mechanics work perfectly well up to a stage, you know. I mean, so it works perfectly well for us here on Earth and what we observe on Earth. It's when you start getting out into space, it kind of has gaps in it, I guess, is the way to explain it, isn't it? It's not that it's wrong, and it's not that we need to replace it as such. We just need to fill in some of those gaps that it doesn't quite explain.
We can say basically Newtonian is a very good approximation for low speeds, much lower than light speed, and not very strong gravities. But when you're around like a strong gravity well like the sun, you have little deviations already. Not much, but measurable. No?
I can't imagine I'm going to be anywhere close to the sun soon, so I'm quite happy sticking with Newtonian for now. But we need to explain this. So
and now we have two different theories. So basically, what is gravity? We said it is a force. Then we said no, the ground is moving upwards. This is weird, but in a scientific theory, also on both theories, we don't care about what gravity is. The question is rather, how does gravity work, or what does it? Because we're interested in the effects.
It's the result, isn't it?
Yeah,
it's always to do with the result.
Because I read also Aristotle and the Greek philosophers. They were all thinking about, why is everything falling down? They had wild theories why it is this way, but I think Newton was the first one who said, I don't care what it is. I just want to know how it works. No?
Which is why a lot of people have said it doesn't matter what you call gravity. Gravity can be called anything. Exactly. You know, you can call it whatever you feel most comfortable with. You can call it magic if you like, but it does work. And obviously, like you say, Newton was more interested in how does it work, as opposed to like the why, because the why could be any reason at all. It was more to do with like, actually, how does it work? Because then I can actually show that it works.
Yeah, and then I can also, we come to this later, what we can do with this. And according to general relativity is basically, this was said, mass tells space-time how to curve, and space-time tells mass how to move. No? And these are different approaches. And in the end, we don't really know what gravity is. This one describes this way. It fits quite well for low speeds in certain situations. Low speeds, low gravity. But with higher speeds, we need this one. And we are not 100% sure, or we have to say we are quite sure that also this one is not complete. There are some weird things going on right now. Also, the James Webb Telescope is seeing things which don't 100% matches our understanding of the beginning of the universe, and maybe also with gravity. No.
Yeah, and I mean, everything on the screen there works in our known reality. That's the thing, isn't it? And
And
that's what you need to remember when we're saying we don't really understand it, or we it doesn't mean we can't use it. You know,
mm,
it works perfectly well within our known reality. But as we
mm,
discover new things, again, where Einstein filled in gaps for Newton, the next stage is maybe filling in gaps for Einstein.
mm. And this is also what very often these conspiracy theorists or flat earthers say. First you said this, then you toss this away and say it's this, and then you're using again this. Make up your mind. What is it? Curvature of
Yeah,
space
yeah,
time or things? To us, it does not matter. We use this one, which describes it the best, and this is basically why we have two theories. This was the older one, and this is the more precise one, but hell of more complicated. No?
yeah. So let's stick with the Newtonian one. It works.
Yeah,
It explains everything perfectly well with low
yeah.
force gravity and mass attracting masses. Works perfectly well in our known reality here on Earth
Mm,
without anything to really worry about,
exactly. And so,
unless we're dealing with a hadron collider. And how many
yeah,
of us
yeah.
do that?
Yeah, there you have to account for it. There you have close to light speed.
Mm,
They reach speeds with 99.999 something percent of light speed. And that's very close to light speed. And okay, I spoiled this one already. Do we really know what gravity is? Answers no. Is our understanding complete? Most likely not. For example, all other forces like electromagnetism, we have an explanation in quantum theory for it, but not
mhm.
gravity. Quantum theory is completely without gravity. we have There are a lot of attempts to find another explanation for gravity, but right now we have only the classical theory from
Yes.
Einstein. This is
Yeah.
the best one we have right now. So then it's the question: what is the theory? Because casually we say when at the place where I work, I go to the freezer and somebody took my yogurt. Yeah, then I say, oh, I have a theory who might have been this. No? So we
Yeah.
use it
Yeah.
basically casually when you're not really sure, but maybe. No, this is basically how we use theory.
I reckon it's this kind of idea. Yeah.
Yeah. And
Not
so
really a scientific theory.
now we come to scientific theory. We call this. And basically, what is the scientific theory? We have explanation for phenomena which we observe and predictions. Yeah. So basically, a scientific theory explains observable phenomena and enables the prediction of future events or its outcomes, including a mathematical model. We come
And
to this.
the prediction is the important bit
Mm,
about
yeah,
scientific theory, isn't it? It's not just
yeah,
like it explains something. It can also
yeah.
predict future events.
And this is not something fortune teller like or some. We come on the next slide also with an example what we mean with predictions, and then testability and falsibility. What is this? Clear predictions must be derived, which can then be confirmed or refuted through experiments or observation. Or example with the falling apple. Yeah, if
Yeah.
you have one apple who's falling upwards or sideways, then your entire theory is gone. Yeah,
Yeah, I
and
mean, we've never seen one
yeah,
move
yeah,
sideways without any other outside force being added to gravity.
yeah,
But yeah, this is, as we explained in the previous stream, where buoyancy and electrostatics don't actually work because obviously, if you're going for density, it could go up and sideways or any
yeah,
direction this is actually refuting any of those
yeah.
ideas.
And this is also basically a helium balloon goes up. And I remember when I saw this the first time as a kid. Yeah, it was wow. Now this is force upwards. This is flying. It was, and I think everyone seeing this first time, we
Yeah,
we
yeah.
we
Helium
are
balloons are
puzzled
just
to see this. And
They're
That-
defying everything that you know, everything you've seen and accidentally knocked off while you're running around the house has always fallen to the floor, and suddenly this
Yeah.
magic colored object is floating on its
And
own.
exactly. And in the last stream, you can go back and look also at this one. We explained that buoyancy works because of gravity. Because gravity, the more dense, heavier air is basically pressing the lighter one up. So it is a downward force which pushes the other thing up. And this is basically buoyancy. And so this does not, of course, if you see something like this, you have to dissect it and look why it happens. And then, okay, we see now the reason. Okay, it is not contradicting gravity. Moreover, it is because of gravity. And forcibility is also your theory have to be in a way that here, as I said, it can be also refuted. I make now an experiment. I don't know if you are very religious, so pardon for this one. When a theist and an atheist speak to each other, the theist will say God exists, and the atheist will say, "Do you have evidence?" No, and then the theist say, "Do you have evidence against it?" Both. Nobody has evidence for each claim, so it is a claim which is not forcible. You cannot force. Yeah, you know what
falsify.
I mean.
Yeah,
falsify it. Yeah, right. And so basically, supernatural things, basically, which nobody saw, miracles, which were not repeatable. Yeah, you remember maybe the Randy who debunked Uri Geller, no? Because these magic things which Uri Geller did under controlled condition, he did not have the power to do this. No? He
which is a little bit skeptical,
somehow
isn't it?
said,
I
"Oh, there's
wonder
negative
why.
energy here, not today." No? And this is all things that so basically they do not
Yeah,
work.
the pseudoscience is always kind of debunkable and very easily debunkable. So it's kind of one of those things, isn't it? In your example with Uri Geller, obviously a complete faker, a pseudoscientist, and he fooled a lot of innocent people. And I call them innocent. I know some people say would maybe say that they're stupid, but I don't see people like that. I never have. I try very hard not to when thinking about flat earthers. I don't think they're necessarily stupid. I think they're impressionable, and I think some of them are
The
impressionable
wrong
for
way,
their own
basically.
personal reasons. But yeah,
Okay.
and I don't think it necessarily makes them stupid. I think sometimes people might be less able to understand things as easy. I for one don't understand things as well as you do, but that doesn't make me stupid. It just makes me maybe less intelligent. I don't know how you look at it. And it is relative, isn't it? Going back to this whole thing of your own relative perception of where you are and how you view it is very different. So you could actually be the least intelligent person on earth, but think you're the most intelligent person on earth because relatively that's how you see it.
Yeah, exactly.
And that I guess is what makes it maybe a little bit frustrating for people who see it something complicated as being very simple and easy. It can be very frustrating when somebody else comes along and says, well, you're wrong, but they can't prove it in any way. And I guess this is sort of why we kind of do this channel, isn't it? Is to sort of go through the actual things that we know. These are the things in reality that have gone through all of this testing and scientific theory. So I'll let you continue.
Yeah.
But I wanted to put that in there because I don't want anyone watching this think that we're kind of bashing people who aren't necessarily super clever, or we're hitting on the flat earthers and all this, because I think there's often reasons why people follow certain reasons, and they can get sucked into things like cults, which in my opinion, I think the flat earth is a cult, but that's a side note. Anyway, carry on. Gravity.
Okay, then,
I thought I'd give everyone a small break and rattle off a load of waffle.
And the next thing is it has to consistency and integration. This means the scientific theories have to integrate diverse phenomena into a coherent model without contradicting well-established knowledge. What does it mean? Basically, this is basically when you say a balloon which goes up, this is buoyancy and density, there's no gravity anymore, which is nonsense. When you basically contradict also well-established knowledge which have been already tested and are most likely true. Otherwise, you have to have a very good argument why well-established knowledge is not true. No.
Yeah, and gravity is the well-established knowledge, which is why the buoyancy or electrostatics don't actually disprove it.
No.
Because it's not actually, although it's trying to contradict it, it isn't actually supported by any actual backing. It's not a coherent model, as you demonstrated.
No. And so basically, I will go now short how scientific theory normally evolve. You make an observation, the apple falls. We know, what do we know? We know the mass of the apple. We know the height it falls, s, and we know that we can measure the time. And so basically we know 3 things about it. And maybe we can put them together. When it falls, I will not go down to the entire math now, but we see the higher it is, the faster it gets, basically, with time squared. It becomes, so basically when it falls from 1 meter, it is not the same speed as if it falls from 2 meters. It's much faster, and it's not even double fast, it's exponential fast. So we see, okay, there is something like this. We call this proportional. And basically, I go now through this very quickly. But in the end, the most important thing is we come to this. And this is basically our prediction. We can, with this formula, and only knowing the height, we know the gravitational acceleration. Here we were able to calculate it. And only by knowing the height, we can calculate how long it does to fall. And now this is the prediction, basically. Now we measured it for 1 or 2 meters, and we saw, okay, this fits. And this predicts that it would match also for 4, 5, or 100 meters. And this is basically the predictions which have to be verified, of course. And basically, this is then your first, it becomes your hypothesis. This is masses attract each other. So this is now Newtonian. And basically, then you have for your hypothesis a mathematical model. There's also more going on, but this is only one part of the mathematical model to illustrate what it's doing. Of course, the difficulty is we have air resistance on Earth. So basically, air resistance becomes stronger and stronger the faster something is. So this would make
this creates your terminal velocity, isn't it?
Yeah, incorrect. We want to know how it's in the vacuum, but at the 1600s and so on, there were no vacuum chambers. How did they do that? They used a sloped plane, and they rolled something down, because this rolls much slower than this would fall. And so air resistance is not a big issue. And you then started from here, you account for the angle, and then you can basically calculate it as if it was falling down in the straight line from vertically down. And this is basically how this experiment was made. And then basically experimental testing and of derived predictions. So basically experimentally under the same conditions, your experiments have to be repeatable. So basically you might have to write a recipe how to make this experiment. and this you write basically down, and everyone on Earth should be able to repeat this experiment. And if somebody does not get the same result, no, they will speak up and say, "Hey, what did you do there? This is not correct." And this very often happens. They are very interesting customers.
Might go out at the weekend with a
Yeah.
ball and a hill and a stopwatch.
And here is written derived prediction. What is this? For instance, we calculated now the time it needs by knowing only the height. But here we have additionally the mass. Where's the mass? Okay, this is meter per second squared. This has no mass. No mass. So basically, this means the time it needs to fall is independent from us. This is the prediction. This is counterintuitive, no? Because of air resistance, but it has been tested with the slope, and also right now also in vacuum chambers, even on the moon, a feather and a hammer, they fall at the same speed in the vacuum. At the same rate.
Which is exactly explained there, isn't it? As the mass isn't actually the thing that makes the difference. It's that calculation, that mathematical model is predicting that it will be that speed regardless of the mass.
Yeah, and this is basically what your model predicts, which you maybe were not aware before. No? And then you say, oh, why mass does not make a difference? We cross-check, and then you cross-check and find out, hey, it's true. No, and the mathematical model. A few words to this one. This is basically in real life. There's no computer running when we let an apple fall down. Now, so basically, this is only something which we use as a tool to describe it. No.
Yes.
And for this one. My math professor would slap me. I would get only half of the points. Why? If you have here t squared and you solve for t, you have two results. It is plus minus this term. Because if you square something, it becomes positive. So it could be negative and positive. But here, a negative time makes no sense. Now, so I have to say, in this case, negative makes no sense. We throw it away. And so basically, we cut the mathematical model down to this what we need. Now, and mathematicians are very sad about this then.
But because they then spend all of their life trying to explain to you how the negative works as well as the positive. Yeah.
And you know,
you need to be very clever for that, by the way.
You know, also regarding relativity, faster than light travel, you know, according to Einstein, it is not possible. Also traveling back in time. But then you hear somebody say, according to Einstein's equations, it should be possible. Yeah, it is possible. And they are right. For instance, these formula don't know time. You can go forwards and backwards. Yeah, the mathematical model does not care, but we know it makes only sense if the time goes forward.
Yes,
getting here minus, and this is basically the same with general relativity. You have also things like this, and therefore you can say also, we can theoretically travel back in time or faster than light. But this is basically what I might be wrong, but if you do things like I told you here in this simple example, where we know my negative term is nonsense, and this is most likely
because you couldn't. We at this current moment in time don't know a way of traveling back in time, even if it is calculatable, if that's even a word. You know.
And one of the next thing you do is iterative refinement. This, for example, you can calculate here the gravitational acceleration, and you make more sensitive equipment to get this more precise. Now, this is basically iterative refinement, and then
so now I need a really nice slopey slope and a
lot of people, a lot of scientists have repeated it, no contradictions, and then it becomes a scientific theory. But there is no institution which say, this is basically what the conspiracy theorists always say, there's in indoctrination with stuff like this.
No, because you can't be indoctrinated to it because
is-
you can go and test it yourself, essentially.
And there's no institution which say this is the theory, you have only to use this and learn this by heart. It is possible that some don't agree with this. But if you don't agree, you have to show why. And claim
And prove why it doesn't work or why it's
intensity does not work. So your arguments basically bounce off this.
Yes, of course.
And so basically it is, you can say, the the general consensus of scientists that they say, this works this way. And then basically you went from hypothesis to theory. And it is not necessarily the final one, because as we saw with Mercury, the perihelion shift, you see something one day which does not match with this one, and you have to think about a new theory.
So the Newtonian theory didn't quite get there, does it? It doesn't explain it, so it needed an additional theory to explain it.
And as I said, these odd things were with the Mercury orbit were seen, and but if your theory predicts the bending of space-time, of course you have to verify it. This is basically like all mass fall at the same rate. You have a prediction which is maybe counterintuitive, but you have put it to the test. And verification of the bending of space-time, the idea was very early on to use a solar eclipse, because the biggest mass in our sun's solar system is the sun. But the problem is it is very bright. You cannot see stars at the same time. But there's only one time when you can see it at a solar eclipse. And basically, this is, of course, much exaggerated, but this is basically how it works. You have the star in the normal, without the sun at night, you would see the star here. During a solar eclipse, you would see it shifted in this way. And this is also very trippy argument of conspiracy theorists, because the sun mass, there are much more massive objects in space. The curvature of space-time of our sun is not that big. And their claim is very often, this is so minimal, how you can know this? No, you cannot measure this that precise. The way basically how you measure it, you don't measure in one direction and say, the star has to be, if you are 1 minute earlier, it's there. No? So it doesn't work this way. But basically what you do is you look at 4 stars, where you know exactly the position and the angle to each other. And the angular resolution, basically the length in the sky to see it, but it's not a real distance, but as we see it basically from Earth. And then here's your star, which might be or is later on visible next to the sun in a solar eclipse. Before, maybe the year before, the half a year before, when you can see this constellation at night, you make very precise these measurements, and then you have the solar eclipse. You make again the measurements, and if you see here a deviation, then you know, okay, then I have here something like this. And in 1919, in the May 29, there was a solar eclipse in Brazil. And it was a British expedition to Brazil, and
we like to go abroad sometimes.
Yeah. And this was basically the instrumentation. This is a telescope, and with a mirror, they were reflecting the light inside this telescope. I don't know where they had the solar filter, but of course they had one.
I was going to say, if you leave it like that, it's going to blind you, isn't it? Jeez.
Yeah.
I don't think I want to look at the sun through a mirror and a big telescope like that.
they tried already, I think, 2 times before to test this, but the first time it was a solar eclipse in Kazakhstan, and German scientists went with equipment to Kazakhstan. Unfortunately, during this time, the First World War started, and German
Yeah, so that probably
scientists,
sort of put a
guys
halt to a few things.
with such instrumentation were quite suspicious, so they went directly to prison. And I think they were released. I heard something they were then released quite soon, but they did not buy. You have to. Hey,
Well,
what are
they
you
take a
doing?
big telescope.
Yeah, I
What's
want
that
to
for?
measure the spending of space time. Yeah, come you're kidding. Yeah, so
Yeah,
basically this failed.
I think come here. We need to have a word with you about this. Here's a nice room.
Yeah, get a white coat and
Yeah.
so and I think maybe 5 or 6 years before they tried it again, but the photograph, they got the exposure wrong. They had no usable pictures. No? Photography at this time was not the same as today. They have to have this glass plates with photosensitive material, and it was quite complicated. So you could get it wrong.
Yeah, if you've ever seen pictures from like that era with where they've taken it on glass plates and stuff, and it's terribly out of focus and not very clear imaging, but it worked for the time,
This is basically this is one original photo which they took, and this is the negative. No, because making a positive makes no sense. You have to use lenses for projection, and you can get distortions, and you want to have no distortions. No? And so they did it on the negative, and you see, this is basically this part here. These are stars, and they knew where the stars are. And this arrow, this is made in later on. This, of course, they did not have PowerPoint.
Yeah, I don't think that wasn't on the next. Yeah,
but I saw already one, but unfortunately did not find it where the original, where they marked where they should have been. No? And basically, the length of this arrow, I would have put the arrow here, but it means the star was basically shifted in this direction by this amount. No? And you see here, they were shifted in this direction. This was the nearest visible, and this was another one which was far away. It was still shifted, and the thing was, it matched exactly the calculation of general relativity. Because there was, at this time, it was not quite sure, does light have mass or not? If you would think
that's
light
worthy of a welcome
mass,
to reality banner.
Yeah. And if you would assume light would have mass, you would have also a deviation. But everything falls with the same rate, so you don't have to know how high the mass is. You need only the speed, basically, of light, and you would have a deviation too. But the general relativity predicts the double deviation, and exactly this one was measured. So
and
was
it
clear.
matched the prediction. Yeah,
Exactly. And so we know, this is basically how your theory proves some counterintuitive things which are predicted by it. No? And the next one, where we can see it also today with the Hubble Space Telescope, for example, when you have a very large galaxy here, it does the same basically like with the sun. The light traveling from here is coming down here, and we have basically the so-called Einstein rings. And this is an original photo from the Hubble Space Telescope, and this is the most iconic one when someone is talking about gravitational lensing.
I've seen this one. Yeah,
and this is a very heavy galaxy, and this is one.
Nightwolf is having to go right at the wrong time. We're looking at galaxies from Einsteinian gravitational fields and everything. But Nightwolf, thanks very much for being here. Go make some supper, my friend. and catch up the rest of the stream when you can. Take care. Thank you.
Yeah. And and you see the distortion here. There is something behind it, and the galaxy which is behind it now. And okay, this is a close-up of the same one, and this is a weird, wired thing. Now,
wow, we're getting into all sorts of like,
yeah, everything is a galaxy basically here, and you see a lot of distorted somethings
sort of
here.
bit 2001: A Space Odyssey at this stage.
Here, this one, for example, it's distorted till here, maybe by this galaxy. No? You have a lot of distortions here, and also these rings, and this is basically, it looks like as if you look through water on stones or something like this. No? It is completely distorted. No, and so this
and that's actually a good analogy, because when you look through water on stones and the water's moving and rippling, it might be a stream or something along those lines, or a pond that's moving in the wind, you get that rippling effect, and that's because when you're looking at the stones, they look like the stones are moving, but it's the light that's actually doing that, isn't it? And this is just an example of that on a very big scale.
Yeah, right.
And like scale. There's not even a word for that scale.
We have no two theories. When do we use which one? Newtonian. Basically, this is a thumb rule, basically. I will explain later why. If your velocity is smaller than 1% of light speed, you can use mostly Newtonian. And if your mass is, this is basically what I got of the gravitational potential, but it has to be a relatively small and homogeneous gravitational field. And general relativity, it has to be faster than 10% of light speed. Then, in any case, you should consider also the relativistic effects. And if you have high gravity, big galaxies or black holes, you need it too. When do you use it practically? And this is very surprising, because this is, as I said, only a thumb rule. And this is where flat earthers always get mad. Oh, one time you say this, one time you say this. It depends on the accuracy which you need. And basically, Newtonian, for nearly all movements, accelerations on Earth, it is enough. The deviations.
I don't think I'm ever likely to travel 10% of light speed anyway, so it should be okay.
And even if you calculate the deviation, it is mostly so little, it's beyond the tolerance of your measuring equipment. So it makes no sense to use something complicated like this. And when this is good enough. And
it's a lot easier to do the calculation for it as well, and because it's more simplified version in that sense.
And here I was a little bit surprised, but also calculation of trajectories of interplanetary probes, so probes which went to Mars and so on, they use still Newtonian, because in our solar system, the solar wind of the sun, basically the particle or the sun, or a little bit imbalance in the thrust, this has a much more bigger effect than general relativity. And and when they fly to Mars, they have to make also course corrections sometimes. And so if there would be something which they would catch with this one, but normally all other influences are bigger than which we would get from general relativity inside our solar system. And you remembered only with Mercury, we saw this little bit of deviation, but still this is so little. When we send probes to Mercury, also we can stick with this one. But now the interesting part comes: special relativity, GPS satellites. They are also not interplanetary.
Surely they're moving slower than an interplanetary probe.
And they
surely.
are in Earth orbit. But each satellite has an atomic cesium clock. The time has to be very precise, because basically what our GPS devices do, they compare the time stamps when which was sent. And so this is very simplified. I don't know the exact algorithm, but basically by the shift of time and knowing where the satellites are, you can calculate your position. If you would not, I wrote it wrong, no? Satellites should be an E. Okay. If you, okay. Yeah. If this would you would not correct,
you could have written it in German, and then we'd all be really
then
confused.
in German, it's also wrong. And,
I was trying to help you there.
yeah. So
Never mind.
and so basically, also very small deviations would drift away. Now the problem is the satellites are quite high. I think 20,000 kilometer, and they are quite fast. 15,000 kilometer per hour or something like this. And you have to account for the high speed and for they are in a lower gravitational field. And if you don't correct this, it would drift on after one day also by hundreds or kilometers. And even after a few days, it would be completely useless. And so here you have to use, you have to correct for this. And the funny thing is, the first GPS satellites they sent to space, they had to switch off the relativity correction factor because it was a military program, and the general said, spanning of space-time, time dilation, come on. And so they had to build in a switch to switch the correction factor off, but they never had to use the switch. So
because it actually the general relativity needed to actually work in order for it to stay in orbit, essentially.
And of course, particle accelerators, you need it. And
I was right with my Hadron Collider. See,
cleverer
than I look.
999% of light speed, so very close to light speed, of course. And cesium atomic clocks, they are very extremely precise. You have to account for the gravitational field where they are in. They are so precise right now. Already a few centimeters can make a difference. This is mind-blowing.
Is
mind-blowing.
This why my sat nav doesn't work all the time?
You can measure it. This is really mind-blowing. And of course, Mercury's perihelion, if you would want to calculate it very precise, we can go with this one. And of course, black hole gravitational lensing does not work with Newtonian. This works only with
as we saw earlier, because of the bending of light in that way, that your eyes will perceive it completely differently. It's exciting stuff.
This is why I wrote this red, because this is what flat earthers always say. No, before you said you use it for GPS satellites, but you don't use it for interplanetary probes. You're jumping from one to one. It depends on the precision you need. And this is the next topic. They always say, you make assumptions, blah, 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 and you basically make something up. But imagine you cutting 10 centimeter carpet for a floor. Your
or
floor
100 centimeters in that sense.
I used 100 centimeters to make the calculation easy. If you cut it 1 centimeter more or less, it does not really matter for carpet. You cannot be
of course
that precise. So an accuracy of 1% is totally fine for this.
You just fold it under the skirting board and you're fine.
You can use this device to measure it. It's precise enough, and they are not very precise.
Tape measure,
but if you have to cut 1 meter of glass for a window, this should be very precise. Now, if it's off by 1%, this would be 1 centimeter. You can stick your fingertip pinky finger out of the window between the frame. No? So
or it would be too big for the frame, maybe.
yeah,
if you cut it the other way,
or,
of course.
or too big. No? And so
Yeah.
here you might need an accuracy of 0.1 centimeter or 1 millimeter, basically. Now, and for this you need. Okay, maybe this one is overkill, but this
Bit
one,
of an arc cut laser cutter, yeah. Okay,
yeah.
yeah.
You need something more. This is the point. You need definitely something more precise. You can also use a steel ruler, no? Because the steel rulers are much more precise than this one. No? But
Of course, yeah.
And
It's
so
a
basically,
rigid ruler of some form will work.
how we generally approach what we use and which theory or which model we use, we first look which accuracy we need. Do we need 1%
Exactly.
or 0.1%? Then we look at the tolerance of our measurement equipment. If you look at a scale or thermometer or something like this, you always find the accuracy, and you can buy a very expensive accurate one or less expensive like this one with a high tolerance. And so you have, for the accuracy which you need, you have to select the appropriate one.
Appropriate, yeah.
And then you calculate how much is the difference by using a precise or simpler approximation model. So basically, you do once the calculation with general relativity, and you do the calculation with Newtonian. If this is smaller than the accuracy that you need, or even smaller than the tolerance of your measuring equipment, you have no point of using the more complex
more
model.
complicated. Yeah, just use the Newtonian one because it works. It fits what you need. Yeah,
exactly. This is the point. And then you select your model, and there you go. And so basically, because they say always this assumption is blah 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 incorrect or something. This is a whole scientific subject. It's basically, it's called error analysis, and this is a subfield of mathematical statistics. And when I started in university with electrical engineering, the first thing we learned were units. We have to use units, centimeter, millimeter, seconds, and so on, kilogram, and to know what we are calculating. The next thing
you learned that in university. I learned that in school. Basic school.
Basically, my professor said, if you don't write a unit behind every calculation, you get 0 points. Because
I'd have failed there. Okay.
Because it could be bananas, potatoes, how much, what. And the next thing is, the second thing was error analysis. So important. It's that important. Because if you measure, you have always deviations. You have to know which equipment to use, which tolerance, and which accuracy you need. Now, this is very important. And especially important is error propagation. What is this? We saw this formula. We have here the gravitational force, we have the mass, we have the gravitational acceleration. For each one we measure, we have an error. We have basically a statistical deviation. It's not possible. If you measure it 100 times, you get very small margin different.
If you dropped 100 apples, you might get a slightly different time if you're using a stopwatch. But if you use something of a lot more accuracy, then it may be even more precise. But there would still be an element of deviation between the times, wouldn't there?
And here basically you have two variables multiplied, which have an error. And the question is then, how big is the error here? Because the errors get multiplied. And there is, we don't go through this. Basically, you have a formula when you add things, you have to use this formula. This is how the error propagate. If you have multiplication or divisions, you have to used to this formula.
Do you make that any bigger? Because it's a bit
Yeah,
small on
yeah.
screen now.
And
Tech.
partly because this is
I mean,
statistics,
it is
they
just
can compensate each other also a little bit. Yeah, if this is too
you
high
able
and
to
this
make
is
that?
too low,
Oh, he
you have
gets excited. Tech. Are you
yeah.
able to make those equations bigger, or are they not really important? Because they're going to be quite small, and somebody's looking on a
Uh,
phone there. If it's
uh,
too much problems, don't worry.
it's not
But
that
basically,
important. It's not
it's a
important.
very complicated
And yeah, and basically the point
but
is
important equations.
we don't guess, we don't estimate something. We look very closely how errors behave, how they propagate also.
Mhm.
And we always calculate an uncertainty in percentage. This is basically the tolerance.
Yeah.
And we look at the distribution of errors. Maybe you've seen the Gaussian standard distribution.
Yeah.
And this tells us basically if we make 1,000 measurements,
Mhm.
68 one would be around this one, and 95 would be in this one. And this is basically experience. This is, but it
Yeah,
has been.
the middle bit is what you would actually take as being correct,
uh,
and the rest of it you'd sort of
and the
throw
funny
away.
thing is, with everything, if you measure how tall people are, you get also such a distribution. And
Yes, of
basically,
course. Yeah.
this is basically a statistical method we use to see is this deviation, is this something we can live with, or is
So
this too much?
you now made me look bad because I said you can take everything either side and throw it away. I didn't mean all the short people and the really tall people would be thrown away. So
No,
the average height in the middle there. Everyone else, yeah,
yeah,
you can go. We don't need that.
I'm average. I mean,
I'm not, so I'm gone by my own statistical analysis.
yeah, but the whole point of this slide is basically to say we don't just take one theory one day, the other day, and we assume something, and then this is enough. We approximate. No, we think. And as I said, this is the second most important subject which we have directly after units. We have to go into this, and this becomes very. This is a very simple example, but it becomes with more complex formulas very complicated, and you have to do this for your diploma because in most diploma thesis you have also to measure something, and
Yeah.
if this is not done correctly, they will rip it apart, because they
And
say
and so
if
for
you don't
so for
know,
something to get to a theory stage, it's gone through all this multiple times.
yeah, if you don't know how your errors propagate, you don't know what your end result is. You cannot. It's useless. Basically, you have to know basically how big is the maximum error, what is the mean value basically, and how much is the uncertainty or the tolerance. No, otherwise your
Which is
result is nothing worth. No.
and this crops up quite a bit actually, doesn't it? When they actually, for example, when you get flat earthers saying that we see too far or the curve isn't there, but actually
Mhm.
when you do the calculations, it's within those tolerances, isn't it?
Yeah.
And that's the
Yeah.
thing that they haven't taken into account, that it's what you expect to see and what's predicted to see
Yeah.
actually is within the tolerance of what you do
Mm.
see, even if you're the flat earther taking the picture. So
Mm.
it's something that needs to be considered when we're looking at any of these things in reality, that sometimes that you can take a picture of something and it looks a little bit different or unexpected, but if it's within the tolerances of the prediction, then it's still acceptable.
Yeah, and also their argument always, the Earth is flat because it looks flat. And you remember I made one slide where I did the calculation, and
Yes.
I calculated with the size of our Earth. If you're 1.70 meters high, eye level is 1.70 meters, you have to look down to the horizon a 400th of a degree.
Yeah,
So
and
you
that's
cannot,
available in our earlier streams. Look up the one about horizons or
and
tech.
your
Put it all
senses
in the
are
math
not
for you.
that precise. Even measurement equipment is not. You need to measure 1/400th of a degree. This is why Earth looks flat.
Yeah, of
And
course. I don't
you
think
can
my
show
eyes
this
are that
by
good.
calculating this, but they say no, it looks flat. It must be flat. And in reality, it doesn't mean anything if it looks flat.
Yeah, of course.
Okay, light speed. This was basically the first thing which regarding special relativity where Einstein started. Right now, this is the value for the speed of light in vacuum. We have to say in vacuum, how fast it is, and this meter per second. Most people, even
We're getting into the big heavy
know what
stuff
it
now.
is. And this is 1, 2, 3, 9. Okay, it's 1 billion kilometer per hour. Am I right? 3. This is million. This is billion. Yeah, 1 billion kilometer per hour. Light
Yeah.
travels an hour that far, basically. And it's damn fast. We say it's damn fast. But I wrote fast on small scale.
It's a lot quicker than I can run.
No, and so basically this means it would travel around the Earth in 7.2 times around the Earth in 1 second. It's damn fast. So basically, for us here, when we switch on the light, it's instant. It's that fast. Our senses cannot measure such.
No,
delay,
and unless of course you're using a candle, and you might sort of see a little bit of it glowing
or you have
more and more. But
smart home where it goes via router. You press the switch, it goes to your router, and then the light goes on, and you have also a delay. But this has nothing to do with light speed.
Of course, no. The actual bit of when the light turns on, it's instant, isn't it? As far as we're concerned.
But it is slow on large scale. And there was also from a physicist one YouTube video. I didn't find it again, and the title was "Why is light so slow?" And okay, this is clickbait, but because it's quite fast. No? So why is light that slow? And it is ridiculously slow on large scale. Now we look at the approximate traveling time of light. Earth Moon, it's 1 second or 1.3 second. This is already difficult. When you see the Apollo moon landing, you realize the astronaut is talking, beep, then they wait, then they get the answer. No, this is basically the delay by 1 second. And if you ever have a phone call, maybe online with a big lag, you know how inconvenient this is. Not so 1 second is you can still communicate via radio, but it is already inconvenient. And
yeah, it does make me laugh actually when people moan about the delay between, like, obviously the example you used there with the moon landing. I've been on streams before, like speaking to people abroad, and get lag. So, think about distances before you start criticizing a little bit of lag.
Yeah, exactly. And so Earth's sun light needs already 8 minutes. So basically, if our sun would become a black hole and go out, we would be 8 minutes completely fine. We would notice nothing. But after
then it all goes drastically wrong.
Then we have a problem. But you have to imagine 8 minutes. It's quite long, and this is our sun.
Yeah, I mean, technically, if it's gone out 8 minutes ago, we'd only just find out about it now. We could be doing exactly what we are now, and we wouldn't know any different.
Yeah. And Earth Mars, depending where they both are on the orbit, it's 3 minutes up to 22 minutes. So basically, if you call them with a problem, 44 minutes later, you get your answer earliest. Maybe they have to think a little bit also. But you see here, when we fly to Mars, as Elon Musk want to do it, communication does not work in the normal way. You have to write basically like SMS or text, something like this. And and you have to be completely independent. Yeah. If you
Yeah,
have a problem,
Zoom calls are
you're
going
on
to
your own,
be a
not
little bit.
no. Yeah.
Yeah,
And
doing our Zoom calls when half our family are on Mars and half of us on
yeah,
Earth, and we're Zoom
it's
calling
very
them and
difficult.
waiting 44 minutes between each sentence. Yeah, it does show that, like, in reality, it's going to be almost
Mm.
impossible to
Ex-
do unless it's completely independent. And when it's independent, you can, once they've lifted off, you basically forget about them.
Mm. And the next one is here, Earth to Neptune. This is basically the farthest, the most outer planet. No? Pluto is not a planet anymore. It is now only a dwarf planet, so Neptune's the farthest away.
Is it though? Come on, that's just.
So, and Earth Neptune is already 4 hours, and Earth to Voyager 1. This is the probe which is the farthest away, and it still works. We still have contact with this, and 22 hours. And this is basically
So that, ladies and gentlemen, is why we don't get a regular update from Voyager, because it takes a long time to get a signal back.
And this is really and Voyager is basically considered to have left already the solar system. But there are some disputes because it definitely left the influence area of the sun where the solar wind goes. So basically now it is exposed to the cosmic, to the pure cosmic rays. But it is still inside the Oort cloud where our comets are come from. So some say no, it's consider this as a solar system, the others. No? So basically, but it's far away, 22 hours.
Yeah, people arguing about flat Earth, and then like the real scientists out there are deciding whether or not Voyager has actually escaped our solar system or not.
Yeah,
everyone has a little argue, don't they? But reality wins.
Yeah, and Earth to Proxima Centauri. This is our nearest star. It's 4.3 years, and this is basically why we say light year. Light year is not a time. I saw already some stupid science fiction where they said that this is a time. But
Yeah,
it's the length. Yeah, this is 4.3 light years is basically the length the light needs to travel. 4.3 years. It needs this length. No.
And so even at the speed of light, a proton, a light particle would take 4.3 years to get from one side to
we
the other.
always have to think about this, what we consider as high speed, and it takes this long. This basically gives you an idea how fast these distances is. So basically, space is not only very big, it's damn empty. It's damn empty.
Yeah.
Already our solar system. Yeah, it's damn empty. Yeah. And Earth's Andromeda galaxy, or the next neighbor galaxy, is already 2.5 million years ago. So basically, the light we see now has been emitted at the dawn of mankind. Yeah, it's thought we were living in caves at this time. I think 3 million years, they say, the first Homo sapiens.
Yeah, approximately. There's
so basically, we were hunters and gatherers at this time. And now we see the light which was emitted at this time. This is mind-blowing, really. This is a completely different area. And this is also the problem when we want to discover other intelligent life forms. It is possible we missed them by a few million years. You do not only have to consider the distance, also the time. There can be a civilization which is 10 million years ahead of us if they managed to survive and did not kill themselves. Or maybe
and has a son that hasn't died. Yeah.
Or 65 million years ago, maybe aliens visited Earth. They saw dinosaurs and thought, "Oh, no intelligent life form. Okay, checked. You check the next system."
And we'll move on. Yeah.
Years. Yeah, it's possible. It's hypothetically possible. And this is the other problem with intelligent life. And so now the historical it's very interesting. Very early on, philosophers were thinking of light speed. Empedocles from Greece, 450 before Christ, he already thought it's finite. It's interesting. And here Aristoteles, 350, infinite. No? And basically, when we go through time, we had different opinions, and even Johannes Kepler, the Kepler's law, which is also basically a lot of the, let me say, the mechanics of the sky, he basically developed, and he thought it was infinite. No? And then René Descartes, one of the great philosophers of France, infinite. Galileo Galilei, he already thought it is finite. And
maybe that should be maybe a poll for the chat, maybe, or in the comments. Did you think it's finite or infinite? But whose side were you on? Because me and Tech discussed this, didn't we? And I said that I went for finite, didn't I? But
yeah,
we'll see if I was right.
Yeah, okay. I spoil it now. Okay. And of course, measurement of light speed. How do you measure something that fast on Earth? And the first time it was measured, I jump now one back. See, 1620, Galileo Galilei. And already at this time, it was possible to calculate very precisely the orbit of the moon Io. This is the biggest moon of Jupiter.
Yeah.
And sometimes it goes behind Jupiter, and then it comes on the other side. You see it again. And he discovered that this changed basically when we are nearest to them and the farthest. He saw a difference. And then he had the idea, this light speed might be finite, and he made his calculation and came to this value. And you see, this value is very close to them. You have to think when it was. No?
It's kind of like difficult to get your head around how far.
Really good. No? And the next one was Hippolyte Fizeau, is a French one.
Hippolyte Fizeau, yeah.
Okay. But he did the first experiment in 1849.
You can call him Hippo Fizz if you like.
Yeah, Hippo. Right. But he was a genius. He had here a light source. This is a half-reflecting mirror, and here you have a mirror. Here the light goes basically through the half-reflecting mirror, bounces off, and goes to this mirror, and here you observe it. Now you have here a tooth wheel. The light passes only if it's in the gap of the tooth. Then it bounces off. If it's not spinning or spinning slowly, it goes through the same tooth back, and you can see it. But if you rotate this now very, very fast, you at a certain point you reach a rotational speed where basically here the light passes, but on the way back the tooth wheel has moved already, and then it's blocked.
Yes.
So basically what you see when you start moving it, you would see it flickering. Flickering at a certain velocity, you see nothing anymore, because
it's a little bit like watching old cinema reels, isn't it?
Right.
It's a similar kind of process, but obviously this is kind of dealing with it in light speed, so a lot faster, because it's not just the actual flickering of a real tape. It's actually light that's being calculated.
And if you know this distance, okay, this has to be not here a few centimeters, has to be a long distance, and this is spinning really fast. You can measure the rotational speed. You can calculate with this knowledge, the distance and the speed, how fast the light is. not because
Yeah.
when you take this into account, when you don't see it anymore. And he came to this value, which is a little bit faster than we have now, but it is already very, very close. And the next one was
It's not bad for a light bulb and
Yeah.
a few mirrors, though, is it? You know,
already a few years later, Leon folklore. I did not really look into this experiment, but it was he used somehow rotating mirrors, and he was very close to ours right now. Now this is very precise already, and
yeah, I guess it's very similar to the tooth idea
Yeah.
with bouncing
Yeah.
light and stuff and rotating it to calculate the distances, but
yeah,
not
so
one that
that
I'm very familiar with. I mean, it was 1862. We've kind of moved on a little bit since then, but it's a close calculation, though, isn't it?
Mm. And 1 second, I have to drink a little bit. My mouth is getting
Yeah,
dry.
tech
So-
gets carried away and just carries on, you know,
Yeah.
because this is why our streams can sometimes be 2 hours long. I'm not sure how long
Oh.
we've been going on for actually.
Yeah.
Hour 45 today. We're doing quite well. But
Yeah.
this is a big
Okay.
subject. There's a lot to
Yeah.
it, and obviously all of these aspects are relevant to relativity, you know, because we're dealing with light and speeds, and as explained earlier by Tech, that's where it fills in all the gaps that Newton can do with Newtonian gravity, or Newtonian theory. And yes, scientific theory, as explained earlier, probably about 45 minutes ago now, but watch everything, repeat yourself, learn. This is all educational. It's how our reality works and why it's sometimes difficult to understand.
Yeah. Exactly. Okay.
So what we're looking at, relative velocity.
Yeah, relative velocity. We have two cars. They are driving head on with 100 kilometer per hour. That's not looking good.
Well, they haven't got doors on their
Yeah.
cars. They're looking out the window. It's
Yeah.
gonna end horrible, isn't it?
Yeah, and here, if they would crash into each other, it is quite obvious. These relative to each other, you have to add this velocities. So basically, from her view and from her view, they driving into each other with 200 kilometer per hour. And I think this is quite obvious, that this is worse than when the other would be standing. No? And this
But
is most likely,
this is the argument for why people shouldn't speed in vehicles, though, isn't it?
Yeah.
This is the direct argument, because if you actually do happen to be, say, overtaking a car or something like that, and you think you're doing 65 miles an hour or whatever it is in kilometers, but you also need to take into account the speed of the vehicle that you're running into, because it's the combined speed that kills you. You know, it's or is your ultimate injury, shall we say? So, or as my wife would put it when she's playing Grand Theft Auto, you have to stop the car and tell the people they've been in an accident. But that's
And now we have another case. This one is driving 100 kilometer per hour, and the other one is coming closer with 150 kilometer per hour. So this is a little bit faster. And they would run into each other. We have a difference now? We have 150 kilometer, and this is in the same direction. So basically, it would hit this one with a relative speed of 50 kilometer per hour. I think this is quite obvious. And we have to, I think this is quite easy to understand. And now we look how light
absolutely,
works. And now comes an interesting thing, light speed and electromagnetism. Maxwell, this is also basically my main subject, made the Maxwell equations. I don't write that down, don't worry. Which explain basically completely magnetic field and electric fields. No? And he already noticed these two constants. These are, how should I say, these are constants, natural constants, one for the magnetic field and the other one for the electrostatic field or electric field. No? And if you multiply them and take the square root and divided and 1 divided by this one, you get a speed. No, and you see already it's c.
You can say no
And,
because I'm
yeah,
like, I agree, whatever you're saying
and
there, Max,
and
because
and,
yeah.
and Maxwell was already. I read 2 different sources. One said he already realized that this is the light speed. The other source say he thought this must be the speed of light because the calculation showed that this is very close to the speed of light which was measured. So basically, when this was confirmed, light is an electromagnetic wave, so it has directly what to do with electric and magnetic fields. No? And we can show also that light is a wave. This is basically how it would look like water. When you put water waves here, you have an interference pattern.
Yeah,
so
I understand.
basically, wave, the high part of the wave comes together with the high part, then you get this, and here they cancel out. And this here with the laser, you can replicate it quite easily. And this is so basically they saw light is a wave. And the oddity with Maxwell is there is a so-called Lorentz invariance. I have to be brutally honest, I don't understand it totally, but I got what it says. And it says already this transformation that light speed is constant in every inertial frame. And this was really surprising because normally we saw this thing with relative speeds. No? And this basically predicts light is always the same speed. And then they thought, light is a wave, right?
Yeah.
A wave needs a medium, right? So
Of course.
water wave. What is a water wave without water? Nothing. Yeah. So it needs a medium. And they called it luminiferous ether. I will call it later ether for short.
Yeah.
And they thought there is a kind of medium which they called ether. And in this the light travels. Basically, we have one reference frame, one global universal reference frame. Yeah, and in this one, this is always constant. No? But we know our sun is moving in one direction, and also Earth is moving in a direction. So you should measure a difference in light speed on the point where you are now. And okay, I should have
That's a better picture.
Here.
Yeah.
Here you have better, and because the sun is moving here, we should drift through the ether, and obviously the light should be faster. With this, it would be faster. Here, slower, and here it would have the normal speed of light, basically. And this is sorry, this is in German, but in English I did not find a nice picture. So basically, the experiment does the following:
no need to apologize.
You put a light here, and perpendicular another beam. With a mirror which is half reflective. Now it's basically you split this beam in two, and 2 exact same distances. It bounces back, and if you are drifting in this ether, one would be faster and the other slower. And here's the simulation, basically. This is basically when you're standing in the ether was thought that you would get this one. And when you're moving through the ether, you should see a difference. Because you're moving in one direction. So you see here, this one, it has to fight against the ether, and it's slower as the other one.
Yes. Yeah.
But what they measured was always this one. In every period of the year, they measured this one.
Yeah, so the first one, just in case you can't see the pointer from your phone or your computer you're looking at. So it basically they didn't find the ether because they only found that first thing where it actually just matched the light speed matched on both sides. So it wasn't slowed down by anything, was it?
And the funny thing is here, the flat earthers make use this, interpret this in a way that the Earth is not moving. And
Mhm.
but even Michael Morley, they did this experiment because the Earth is moving, because they
Yes.
have enough evidence, and therefore they wanted to test if it is like this or like this, because they thought there is an ether, and they did the experiment over and over again, and they said, moving in this direction, and the ether should not have an influence. And I'm not sure if they both came to the conclusion that there is no one, but this experiment led to the conclusion basically that there is no ether. Light somehow is a wave which propagates as an electromagnetic wave through vacuum. But what is the implication of the constants of light speed, which was predicted by the Lorentz transformation, and later on also it was shown, okay, ether does not exist. What is the implication? So if we look now, Earth is traveling with this velocity around the sun, and head on the light of a star, stars obviously farther away, with light speed, c, comes from this direction.
Mhm.
And from the other direction, light speed comes also with c. And according to Newtonian, the resulting speed, this is like the two cars which were running head on each other.
Yeah.
You have
Yeah.
to add both.
Yeah.
This one, it tries to catch up with Earth, so we have sees the larger value, so we have to subtract the smaller value, and this would be, in the end, this would be smaller than this one. This is basically what this means. This is bigger.
Which is the same as the car driving into the back of the other car. Yeah.
And the constants of light speed, which was shown by the Lorentz transformation and shown that no ether exists, basically, this was then, according Einstein is wrong, basically, at this time. It should be rather according Maxwell and Lorentz, but okay, we go now with Einstein, is the thing we would measure would be c, so this light would be not this one added to this one. And also the light from the back would be also c, and so basically both speeds would be equal c. This is basically what the Maxwell formula with the Lorentz transformation predicts, and this is basically what has been shown also by the Mack-Moore experiment, that there's no influence with movement anyway. No. And what are the consequences?
It's difficult to get your head around, isn't it? Because obviously it's not as intuitive as the cars driving into each other.
No? And we come later on also how it was verified. But first of all, Einstein was living, I think, next to train station. Of course, this kind of train did not exist at this time.
No, not unless he traveled in the future.
And he made a thought experiment. He said, okay, here are two guys standing on the train. The train is not moving. He switches on his flashlight, and both see the light flying with the light speed. And we call this time now time 1. And now we let the train move with 100 kilometers per hour. So both would also travel 100 kilometers per hour.
Yep.
They would still see
our video motion to understand that.
Yeah. So when you are inside the train, you don't realize that you are moving. It's an inertial reference frame, and so you have the same time. But now we have an outside observer, and we learned c is always constant, independent to your reference frame. This means, according Newton, he would expect that light would travel with 100 kilometers per hour plus c when he looks at this.
Yeah.
But it is traveling with c, so 100 kilometers 100 kilometers per hour slower than expected.
Yeah, because of course you think that it was moving with the train and C, train is doing 100 kilometers an hour, C is doing light speed, so
Mm.
it should be light speed plus 100 kilometers per hour, which obviously you can't technically do
And
because you can't
and
accelerate
they
light speed.
yeah, and he sees too with C, but because the train is moving, he was initially thinking, okay, it's 100 kilometer per hour plus C. They're moving with 100 kilometer per hour. I should also see the times 1, no?
Mhm.
But he see it 100 kilometer per hour slower. What does slower mean? Slower mean it takes a longer time. And this time too he sees. So basically, what happens now is time 2 is larger than time 1. And this were where Einstein said, if C does not change, we don't know why it does not change. Yeah, there's no. We see mathematically that is with this transformation it works this way. We don't know why nature made this like this, no, but it is a fact. Light is always constant. And he said, when C stays the same, then the time has to change because he sees it takes longer than they see it. And
Of course, yeah.
so this is time dilation. According special relativity.
That's where the phrase comes from, yeah.
Yeah, this time dilation. And this is basically the basis of special relativity is the constants of light speed. And this is basically I said it already. No? If you understand this one, this is that light for reasons unknown is constant. Yeah. Then basically, if the if the speed doesn't change, the time has to change. And my wife, I was explaining this to her the other day, and she said, "Do you understand this? Why it's always the same?" I said, "No, I don't. Nobody understands this, but I got used to it." So, this is basically like the apple falls from the tree. We're used to seeing this, so it is normal for us. No?
Yeah,
And
and the thing is that this isn't just a case of like we're used to it, so we accept it. This is all proven, isn't it?
and
This is all
this one
calculated.
exactly, and this one we don't know why the apple falls down, and we don't know why C is always the same. It is a fact, and we have to live with it that we have time dilation.
Yeah,
And
whether we can fully explain it or not, it is a thing. It's part of reality. We can bring up our welcome to reality banner for that one. I think because it is it is just one of those things.
yeah, and so this is a wild prediction, right? So of a hypothesis, so we have to test it. And the Heffley-Keating experiment was carried out in 1971 on an airplane, and this airplane was equipped with 2 cesium clocks. They used to in order that to see if maybe one is faster than the other. So it's basically to cross-check. And this is why they took 2 cesium clocks with them. They are the most accurate clocks still, and they were flying with this aircraft 2 times around the Earth in one direction. Okay, they had to refuel because planes cannot fly 2 times without refueling. No? But they were flying 2 times in one direction and 2 times in the other direction. They did this in 2 different directions to cancel out if there would be anything not symmetrically or something like this. No? To cancel this out, they flew basically 4 times around the Earth, 2 times in this direction, 2 times in this direction. And they had,
let's get
and
rid of the banner. Hold on.
basically they made the calculation. They are higher than on ground, so they have to account for general relativity, the curvature of space-time, and special relativity because they are moving quite fast. And these 2 speeds theoretically calculated added are this what here 40 point, and this is the uncertainty And this, you see here, this is what I said. You have always a tolerance. No, this is the tolerance basically of these two machines. No, and the thing which they measured the difference. Yeah, you see, okay, this looks bigger, but it is here 10%, 10 plus minus, and this 23 plus minus. No, so it is within the tolerance exactly eastward like predicted. And here it's a little bit closer even, but this has nothing to say. Yeah, this is inside the tolerance. So, and this is inside the tolerance. It could be in incidents. Yeah? So, as long as you are in the tolerance of your measuring equipment, you've verified it. So basically, they returned back from this trip a little bit younger than the rest of
Of course, yeah.
but nearly this is nanoseconds. This is basically a billionth part of a second. So it's these things are very
that's something you need to like actually realize that in case somebody was looking at those figures and didn't actually catch that it is nanoseconds gained that we're measuring. We're not talking about 10 seconds and 7 seconds. We're talking about nanoseconds. And those differences look quite big, but when you're looking at that in nanoseconds, it's nothing really.
Yeah, but it is in the range of the uncertainty, the tolerance, and within the tolerance, you get it exactly as expected. No.
Yeah,
and the next one is the muon lifetime experiment, and we have very fast incoming particles of the sun, or also how is it called? This cosmic rays. No, when they hit the atmosphere, they scatter into different particles, and one is basically the muon, and the muon has a lifetime of 2.2 microseconds if we basically produce it on Earth. When we split something like this, 2.2 microseconds. But this one, we can measure down on the surface, and it survived 22, so 10 times more microseconds. And the reason is it's coming very fast in with nearly light speed. And this is the reason why it still lives, because for the muon, the time goes slower. So basically for him, this did not expire for him. But we see it with surviving that long. This is the reasons, because their clock is going slower.
Yeah.
So we can measure it on Earth. And this is basically another part of evidence. Then there was also an experiment, gravity probe A and B, one in 1976 and the other in 2004. A had a cesium clock, and this was compared to a clock on Earth. You had basically to account for it's higher in orbit, so lower gravity, and the speed, of course. And the time dilation they measured was within 0.02% of what was predicted of general relativity. So very close. No,
that's pretty darn close.
Yeah. And another one, I'm not quite sure how it worked with gyroscopes, and this was launched in 2004.
So they electro gyroscopes, or
with gyroscopes, and with this one they could measure the bending basically of space-time around the Earth, and they got it in 1.01% of what was predicted. So very, very close. And
that would come into it being a success.
Yeah, completely. Now this is basically below the measuring within the measuring tolerance. And so it can be considered as verified. The other thing is the NIST this is an aluminium atomic clock. This works somehow with an aluminium atom. I don't know, but it's the most precise clock in the world. And
It's a bit
if
big
you
to go on your
do-
wrist, though, isn't it?
And with this one, you can measure gravitational time dilation. And I'm not really sure. Oops, I'm not really sure. This is why I did not write it down. It can detect a time difference of a few centimeters. If it's higher, a few centimeters, or lower, a
Oh,
few centimeters.
that's like a very
It's
short distance to be
incredible,
calculated in time.
and this is why I did not write it down, because before I heard the closest one was 7 centimeter, that you can
Mhm.
measure the time dilation of one clock is higher 7 centimeter. But this
Which is incredibly fast, in order
one
to be able to measure that.
was also in a fraction of a centimeter. But I'm this is why I did not write it down, because it is still for me unbelievable. But even 7 centimeter is incredible accurate.
Is it are the red glasses, are they obligatory for this?
No,
Do you have to wear them? Yeah.
no, there should be. Yeah, it's something. It's always with I think
This is
this is for
Space
the
Hero suit.
they use light basically for the comparison. If you put basically light beams from both together, you can measure an interference, even a very slight one. I think this is basically how they compared it. Now the comparison was here basically, of course, a very precise clock, but the comparison method was key here. And we had this before. The global positioning system works with it.
Yeah.
And
GPS.
as I said, without it, it would drift away within days beyond usability. And right now, there are different sources. I've found something 31 active satellites. Each one has a cesium atomic clock.
Mhm.
The orbit is at 20,000 kilometers, so much higher than low Earth orbit, not so quite
Yeah.
far away from Earth. And
That is quite a distance,
yeah,
isn't it?
14,000 kilometer per hour. It is slower than low Earth orbit. Space shuttle and space station, they travel with 27,000 kilometer per hour, because they are lower, gravity is higher. Yeah, in order not to fall down, they have to go faster. No? The farther away, the slower you have to be to stay in orbit. But you need, of course, more energy to go up. Now, this is
Yeah,
clear.
and you need to like, maybe make it clear that they're not talking about geocentric orbits at that speed, are they?
No, no, and they have to.
Just in case somebody was thinking that might be the case, that
Yeah,
they're not actually geocentric, which obviously means
no,
that
yeah,
they're not in direct line of
they're not
sight to the exact
geocentric.
spot on Earth all of the time.
I think geocentric is is about 30,000 kilometer or something, or
Mhm.
50,000, something. This range is a little bit higher, and then you basically, when you're over the equator, your orbit is as fast or as slow as Earth's rotation, so you're basically always over the same spot. And this is basically our TV satellites. They have to be the parabolic antenna you put at one spot, no? And because they virtually are always at the same spot in the sky, you don't have to change the angle of the antenna always, no? Yeah.
Yeah, and it also means that the studio doesn't have to change anywhere or move
Yeah.
around the Earth. So
And then, oh damn, I did not do the animation. I spoiled now everything. Okay. Oh, I forgot this. Okay,
well, we'll have to
everything's
scrap it,
ruined here.
start
Okay.
again. Yeah, it's
Yeah.
all gone.
We
Yeah,
have to
forget it.
start from the beginning. Oh,
Hold
no.
on.
So
Can we use some of this general relativity and go back in time somehow?
yeah.
Yeah.
Yeah, no, it's not possible. So is the light speed question mark? A stupid question, no? First of all.
Okay.
But if we use light, if light goes through a medium, it becomes slower than C. No, in a more dense medium. And I remember when I heard first, this was when I was 16, 17 about the constants of light speed. And then in school, we learned refraction. And I first said, no, it's not possible. Light always travels as c. But it is true, in this medium, it is slower. And this is also one of the reasons why it bends. This is the wavefront. And because it's slower here, and the wavefront does not rip apart. So this moves slower and this faster, and so it bends basically down here, and here goes basically there. And in this case, in a dense medium, other things can be faster than light in this medium, because light is slower than c. No? And this is an example. This is the Cherenkov radiation. This is a nuclear reactor. And this is no CGI. It really looks this way. And these blue lights are electrons, which are faster than light in this medium water. This is in water. No? And yesterday we wondered also why here the stairs are here. I won't go down there. And
no, we decided that we want to turn it off and wait a few hundred years and then drain it first. But yeah,
it looks really crazy. It looks out of the world, but it really looks this way. And but the electrons are still slower than c. This is the vacuum light speed. No, so they are still slower than this one, but faster than light in this medium. And they react with the water around it, and this is basically where you get. It's basically like a shock wave of a supersonic plane. They emit light now by hitting the other atoms.
It's pretty spectacular, isn't it?
Yeah.
It is. I mean, when you actually look at that, I mean that.
And basically C is basically not light speed. Light travels accidentally at the same speed, and it has no other choice in vacuum. We come to this in a few minutes after the slide, why light has to travel with light speed. C is the speed of causality. Nothing can propagate faster. No information can travel faster. So goodbye to subspace communication in Star Trek. It's not possible. Causality cannot propagate faster than C. And they did.
Well, if you're going to start dissing Star Trek communication consoles, we're going to have to end the stream, I'm afraid, there, because you can't do that. You can't say things like that aren't real.
One reason why I became an engineer is also because I watched Star Trek, and now I realize it does not work.
And Tech went, nope, that's wrong. I'm going to correct all of it and become an engineer.
I still prefer the originals than the. Next Generation was also okay, but the other ones where they make this pseudo tech talk, it's such nonsense they're talking. I don't like this. No?
it's called really science fiction nonsense. For a reason, Tech. Don't worry.
But the original one, they're really, really great. But also, only Picard in Next Generation, this was also okay. So basically, it's the speed of causality, and a lot of things have been tested to be faster than C. Quantum tunneling, quantum entanglement, which happens instantly. But the problem is, we maybe this is for another time, but somebody who know about quantum entanglement, it happens at the same time on both ends, but you don't know, you cannot transport an information because the result you get is random, the end get random. You have to come together the fastest is light speed to see what you get. No?
To move from point A to point B.
Where everything has been done.
Yeah, because essentially, to break it down, and if I understand this correctly, with light speed, you've got point A to point B, but with the quantum causality, you've got point A and point A, haven't you? Essentially, it's just on, and that's it. It's instant.
It is only possible with fastest light speed. Faster is not possible. A lot have been tried, but It's
Yeah,
and
because
this
there's
one,
no way of actually sending additional data at that
and
speed.
this
That's the
there,
problem.
there are a few dogmas in basically the only indoctrination by nature is C. Nothing can travel faster than C, and the other one is conservation of energy. This is why we
Yeah.
don't have perpetuum mobile machines, no, and so free energy. This doesn't work. So conservation
Yeah,
of
listen
energy,
up, free energy people on X.
yeah.
If you post any more free energy things,
And
we're
see,
gonna.
this are basically you can try everything. These you cannot break. No. And now, why does light travel in vacuum with light speed? We learned light is an electromagnetic wave, only energy, no mass. Now we make a thought experiment. By the way, this is my idea. I never saw this before. This is how I made a thought experiment to because I heard or I read it somewhere that light, everything which has no mass. Right now we know only light has no mass, but has no other option to travel at a different speed than light speed. No? And I thought, why is this? No? And then I made a thought experiment, and this is this one. So it's a premiere.
So
We have,
get ready in the comments,
yeah,
people.
we
You
have
know.
we have 4 different balls. Yeah, and yeah, okay, they have the same size. They get lighter and lighter, and this one has no mass virtually. No? If we light has no mass, okay, yeah. And now we kick this with an impulse, with a momentum. Yeah, momentum is mass multiplied with velocity. We call it p.
Mhm.
Is basically momentum. So you have to imagine you kick them. We can say also it's a force. It's a bit different, but all with the same momentum. You kick them. Yeah. The
Yeah.
first
So
one.
we're applying a force, which in
Mm,
this instance we're calling a kick.
So basically, if we solve this one for v, so this is the kick, the momentum divided by m is the velocity. We do it with the first one. We do it with this momentum. This momentum is 10 kilogram multiplied by meter per second. This is the momentum, and the ball mass is 10 kilogram.
That's a fairly kind of like just a
Yeah,
normal kind of kick, really, isn't it? 10
yeah,
kilograms of velocity and
yeah.
force.
If we would kick this, we can, when we calculate this is division, 10 divided by 10, so 1 meter per second. This would move. Oh,
That's me playing football.
yeah. And now
not very quick.
we make the ball lighter, but we kick it with the same momentum. Now we have
Okay.
5 kilogram. So
I've
what
got a
happens?
better chance of making the school team. Go on.
5 divided by 10 is 2 meter per second. It's double fast.
That's not too
Yeah.
bad. Yeah, I might make the school team on that one.
Yeah. And now, again, with the same momentum, but now it's only 2.5 kilos. Then it goes much faster. It goes with 4 meter per second.
Now we're in the FA Cup. Awesome.
Yeah. And now you have to think, you make this smaller and smaller. We see the smaller the mass is, and we kick it with the same momentum. It goes away fast and faster, the smaller the mass. So this is now M for mass. Here, this is meter. This is sometimes a little bit confusing because it's the same letter. But now, if we think this mass would go to 0,
Yeah.
this velocity would become higher and higher, and eventually, pure mathematically, it would be infinite. And
that mean my prediction was wrong from earlier about saying it was finite?
But our experiment says nothing's faster than light. So basically, if the mass goes
So
to
it's
0,
finite, and I was right. Yes.
So this one is kicked away by C. And you have to see an electromagnetic wave is always emitted. Yeah, you have energy, particles, or something, and light is emitted. And so basically, it gets a momentum. Yeah. And even if it wouldn't get a momentum, it would materialize in space. Somehow, the smallest gust of wind or something like this would give it a kick. And the smallest kick already, when you have zero mass, accelerates it to light speed.
Yeah, it would already reach light speed just on having any amount of force applied to it. Yeah.
And this is the explanation why something with no mass has to travel faster than light. Okay. So basically, this is most of what I wanted to show. Here I have also some cool images of this light bending. We saw this and this and this.
Yes.
And now we have a very interesting one. We see bending. We see here also distortions. Now we see some galaxy like this, but it is we can calculate very good with the brightness how much mass this has, and this did not or does not align with the distortion. The distortion is much stronger than the galaxies in front. And basically, this is a visualization how the masses should be to make this distortion which we see.
Wow.
And this is basically what...
That's my surprise noise.
This is dark matter.
Yes.
And we have no idea what it is. And there were also some suggestions that maybe general relativity on larger scale is different. And they made also adjustments to the theory, but it does not really work. And every galaxy seems to have dark matter. They all rotate, these spiral galaxies, faster than they should. Normally, they rotate that fast that it would rip them apart. But don't. So there must be much more mass out there. And there were some suggestions that general relativity is not the end of the story, but they found now galaxies without dark matter. So they were rotating at the correct speed. And so if we have galaxies which turn faster as they should, and we have galaxies they turn as fast as they should, there must be something different. The theory should be according this right. There must be something what we can't see, and it's much more than the universe of dark matter than matter which we can see and we are made of. And this is basically how this is one of the visualizations where we see that the bending or the gravitational lensing does not align.
Yeah, I don't think we can
this is
get
another
into the maths
interesting one. You
regarding
can
that,
also
that's the dark matter.
calculate or reconstruct. Here we have one galaxy behind this one, and it's stretched like this. And this is the most likely the position. And if you put this a little bit together with the right math, you get a resemblance how the galaxy would look like, which is behind here.
Wow.
No. Yeah. And this
now see that now we're back to black holes.
All
black holes look really simple, don't they?
Yeah.
You know, this image looks incredibly simple after we've gone through all that.
And as I said, this was the visualization of Interstellar and the most likely as we think it looks like. And here it's a little bit visualized. This is coming towards us, and you have normally a blue shift. It is more. This is why it's wider, and here it goes back. It goes black because this goes away, or red, infrared,
and red shift. Yeah.
So this is why this one is brighter. And now I have to look here in 2019, the first time with a real big effort, a lot of radio telescopes were able to measure, not in the visible light, but in radio waves, it was possible to image the first event horizon of a black hole. And maybe you have seen this, and this is how we saw it through the Event Horizon Telescope. And
which is showing that blue and red shift, isn't it? Essentially, you got that lighter part and that darker part.
So basically, in reality, these are radio waves. This is not visible light. Now, they are colorized in order to see this. No, this is radio.
Thanks for that.
Yeah, and
so there goes my theory.
We see, but we see here a bright part, and it looks, because of general relativity, this is a massive black hole in the center of the galaxy M86. 55 million light years away, 6 billion times the mass of the sun. And this is basically the picture I showed in the beginning. And this teeny tiny thing here, they were able to image. And this is basically how it looked like. And the dark thing here basically is the event horizon.
Mm-hmm.
And if I turn it a little bit, you a little bit see the resemblance with this visualization. You see here the bright part, and here it becomes darker. No?
See, so I was on the right track. There you go. I'm not
the
as stupid as you think.
Is, from all direction which you look, because of the bending of space-time, you see a ring. Yeah, according to Newton, you would maybe see here only the rim of it. On the other one, you would see the disk. But with general relativity, you see this. And basically here, as we said, you're looking over the black hole. And this is what you do here. You're looking basically over the black hole. And so it basically looks like as we thought.
It's an incredibly good image considering how far away it is.
And this is the second one they imaged, which was much difficult to image. This is Sagittarius A star. This is our black hole in the center of our galaxy, of the Milky Way. And this one...
Don't worry, we're not falling in it just yet.
And it is much closer, but it is smaller than the other one. No, it's only 4 million times the mass of the sun. It's still big. But the problem is a lot of stars are in front of this. We're looking towards the center of the galaxy. It's very difficult to, and with radio telescopes, it's possible. And because our black hole is smaller, we see the rotation of the thing, of the mass is faster. And it was very difficult to image this. And this was the closest what they get. It is not quite clear what we have 3 here. Maybe it's the same thing, but it was rotating or something like this. No? But here, the important point is we see also the darker spot here.
And it's good to remember that like these images are like taken a very far away, and it's very possible that because they're so far away, you've got like the actual multiple images maybe at the time that it took to take the pictures to capture the light, even at light speed that far away, it would have had time to potentially move in the camera's frame of reference, and that's why it could be an explanation for why you have those 3 like, or it could be 3 aliens just hanging out. But until we get there, we're not ever going to like really be able to 100% answer why there's 3 images there, or 3 light sources, radioactive or otherwise.
The size comparison. Basically, our black hole in the center of the galaxy would fit into the Mercury orbit. Now this is how large this is.
So big, and this but not crazy.
And this one would fit in here, and this would be Pluto orbits, and this would be Voyager 1, the farthest away spacecraft. So this is so big, and you have to see here. This is micro arc seconds. This is basically the angular resolution, and this is much far away.
I hope everyone can read that behind the StreamYard logo. Unfortunately, we're not monetizing anyway, so we're still using freebies. But I can read it. That it's obviously saying that it's
This
a
is
micro
basically
arc-second.
only 27,000 light years away, and this 55,000. And this is basically as we would see them in the sky, theoretically, at this distance. Now, this is so big. No?
It's pretty whopping. Here's just a normal CGI image for you to kind of get your head around.
This is a visualization, and because matter moves around the black hole, and with the velocity which can be measured with radio telescope, you can also basically calculate how big the event horizon of a black hole is when it's too far away to see, because you see it by the orbiting things. And here, this would be our black hole, and this is this one. This is the largest one.
So our nice little Sagittarius A is just like completely swallowed up and disappearing, then, isn't it?
Yeah. And this is basically ours. And one thing I want to address, they say always that the event horizon, this black thing, they say always gravity is so strong that it even attracts light. This is nonsense. It can there cannot be a force because light has no weight, has no mass. No, it follows the curvature, and the curvature of space-time, the infalling space, is basically so strong here that there is no way out. Yeah,
you remember even light image gets trapped in there.
Yeah, it's trapped. You have to imagine the video which I showed where the space was falling towards it. At the event horizon, it falls down faster than light speed, because the only thing which is faster than light speed is space itself. Space itself can contract and also become bigger with light speed. This faster than light speed. This is completely in line with general relativity, but nothing within this space can travel faster than light, if this makes sense. And here, basically,
it makes sense to me, but I know what you mean.
And here, the space basically starts to fall in faster than the light can go out. It cannot, because it struggles, but it's too fast. And this is basically the event horizon where nothing can leave the black hole anymore, but not because it attracts even light. It does not attract it. There is no way out because of curvature of the Yeah. And this is basically how they did this. They coupled around the globe a lot of, I think in total, eight radio telescopes. And they switched them, of course, the Earth turns. They directed at the same spot in the sky. And then when it turns, they had to switch to different ones. And they have to measure the same thing at exactly the same time. Otherwise, you cannot put this image together. And they collected a lot of data. 8 radio telescopes, 1 week of multiple simultaneous observations. In total, this is the data rate. They got 5 petabytes, 5,000 terabytes of data collected. And the funny thing is, in order to bring this, I think somewhere in United States, they processed the data. They had racks full of hard disks and shipped them with a plane. They flew them in with a plane because by plane it was faster than via internet or
downloading 5,000 terabytes
of data to transfer the data. It was so much data. It was faster to put it in a plane and fly it in there.
I mean, geez, we moan about internet speeds now, but you imagine waiting for 5,000 terabytes of data to download. You'd be like, I'll just go to the pub for a while, I think.
And basically, you have here a spot around, and basically with this, they had a virtual telescope which has nearly the size, which has the size of Earth. And with this size, it was possible to image this. Now, otherwise, it's not possible. No radio telescope in the world is big enough to capture something like this, but they all together on different places got the resolution needed. No.
And
And
that's that. In all fairness, Tech, we need to like show that is a feat of mankind, isn't it? To be able to think of being able to do that. You know, that they're basically using all of those telescopes together simultaneously to create a one massive telescope that's big enough to get out there and view these things, and to be able to like then angle it in exactly the same spot at the same time is an incredible achievement.
And now we saw how strong gravity can be. In the last stream,
Black hole size gravity, yeah. Ooh,
we already saw that gravity is the weakest force. Yeah, electromagnetism is much. It's 10 to the power of 36 times. So basically, a 1 with 36 zeros stronger than gravity. But you have plus and minus, so it cancels each other out. Yeah, and the force is even so strong. Yeah, you see a lightning. You know, when you have the separation of plus and minus, it is so strong it wants to come together again.
Just one sec there for you, Tech, because I don't know whether you're showing it, but your screen is froze. So I think it's okay as far as the stream is concerned, but your whatever you're presenting is frozen on that image. Oh, there we go. I think we might have moved it across now.
And so basically, as I said, gravity is the smallest of the four fundamental forces which we know so far. And I did this in Newtonian. So Earth's rotation does not count, but basically I realized I wanted to calculate how much the gravitational pull, it is no pull, but the inertial force is of the sun traveling around the galaxy and Earth,
galaxy, the Milky Way.
And I realized I made the calculation already when I was calculating the centripetal force.
Yeah, we saw this in our motion one, didn't we?
This is the time, because according to Newtonian, and this is much slower than light speed. Yeah, so we can go Newtonian with this. But what I realized here, and this is why I brought in this slide, you are in an orbit according to Newtonian when your centrifugal force is equal to your centripetal. I calculated so basically the centripetal is gravity. So I calculated this. So basically for Earth's rotation, we know this one, but here Earth around the sun, gravity of the sun, which our Earth experience at this place, is 0.06 times less than the gravitational acceleration on Earth.
Acceleration on Earth,
and this is amazing. This is so tiny, and
it's nothing worth worrying about, is it? Jeez.
But the math works out. The math works out at this distance with the speed we are traveling. We're traveling with this one here, 100,000 kilometers per hour around the sun, tangential velocity, but the rotation is 1 year, so the rotation is slow. Yeah, but the tangential velocity is high, and the math, as I said, I calculated it works out. Yeah, with this teeny tiny pull of the sun, we stay at this distance in orbit. This is really amazing and counterintuitive, of course. Not counterintuitive.
Yeah, because you'd expect it to be a lot larger in order to pull the Earth along.
All other forces,
in reality, it's
electromagnetism cancel each other out. Yeah, so the only force remaining is this one, and if only one force remains, it does something to you. And this is why we orbit the sun. And now you have to imagine, and this is around the Milky Way. It's even much smaller than this one, no? And this is really surprising and counterintuitive. But as I said, it works perfectly. You can calculate this. This little pull is enough. And now you have to imagine how much mass you need to pull in the space so far faster than light, which how much you need to make this weakest force basically the strongest force.
Wow.
This very strong force of a black hole. This is the
So
crazy
basically, people don't mess with black holes. They're big and scary.
Yeah.
And they will suck you in faster than light.
Yeah. Basically, that's
Right.
it. I don't want to torture you with the next one, but
we've done a solid 2 hours and 44 minutes so far. You know,
this is too much now. This is regarding tides and the tide. This is basically the same. The explanation why we have tides not in a teacup, but in the oceans. Despite
maybe we can look at this in Gravity Part 3 then, you know?
Maybe we put it in another one, no? And only to say one thing, the tides are not because the moon's gravity is pulling the water up. It is squeezed basically upwards. You have all these red arrows, they add together the horizontal component, so it's squeezed more upwards than attracted upwards. And this is basically the reason why in the coffee cup you don't have tides, but in the ocean, because a small force multiplied with a lot of ocean is a lot of force. And this squeezes basically this one up here, and also at the same time here, but this is a bit complicated. This can we do another time.
Maybe we can look at it like at another time then.
Yeah.
Like tech, because obviously that there's a lot to this, and a lot of explanation that probably will need to be looked into.
But this is basically why moon gravity is also, I think, 100th or 1000th of Earth gravity. And flat earthers say, you can calculate it, the moon is so far away, it does not have an effect. But when you do the math and consider not only the force in this direction, but the squeezing force, small force multiplied with a lot of mass is a strong force. And in the teacup, you don't have much water, so there is not a big force.
Not gonna happen.
This is basically to mention this one because it's related to gravity, and basically that's it. No.
Well, thank you very much. Let's bring us back on stage there.
Yeah.
I hope everyone's managed to follow all this. It's very complicated. But
it is.
We've dumbed it down so I can understand it.
And
you know,
and here also. I have to be honest, without the flat, I'm somehow frozen.
You are somehow frozen. Oh, do we need to give you a mild kick? Shall we give you a little kick? Shall we? I don't know.
Yeah. So this time dilation. I'm now moving.
Oh, could be. You're moving faster than me, and therefore you look frozen. Darn.
Yeah. And maybe one fun fact.
Okay.
One fun fact. I think this one is funny for everyone.
Okay, let's bring that up for you. 1 second. So
where's my comparison? Where
is he looking for it? He's looking for it. Hold on. Let's see if we can.
Here.
Let me know when you're ready.
How long? When you imagine you are a light particle, and am I still online? Can you hear me?
Yeah. We can see everything. I've put your screen up again, but your camera is still frozen for whatever reason.
Okay. So. This is maybe here a problem I have with. Never mind.
It's a late night internet speeds.
Yeah. Now imagine you are a photon and you're traveling to Proxima Centauri. From Earth, you're traveling 4.3 years. No?
very little mass.
How fast would you be there when you would be the photon? Yeah, you have time dilation.
Well,
the answer
yeah.
is instantly, because light at light speed the time stands still. Time dilation is so strong, time stands still. So basically, light for a photon, it doesn't matter where to go. Yeah, it is instantly there. But we would see it, and this is basically the counterintuitive thing. We would see it traveling 4.3 years. No? But for light,
Yeah,
it's always
but
instant.
for itself, it would just be instant.
Yeah.
Well, I'm going to bring back the frozen instant proton TechTranslate, who's
Yeah,
just like turned
checking
into
what
an
happened.
image now. I don't know. It's something to do with your light speed internet, I suspect, but I think we can leave it there without any kind of fear.
Sure.
It's still a good image of you there,
So
Tech.
I,
Oh, there you go.
yeah.
There you go.
I
No,
thought
that
when I
that
give it a
didn't
click,
help.
it didn't help. Okay.
I mean, I can drop you, but I don't think that's very fair either, you know. So maybe we don't do
At
that
least
either.
I'm doing not. You catch me not in a very silly facial
Yeah,
expression.
exactly.
This
Yeah,
at
you can't really
all
clip that. You just look like
yeah,
you're just interested in what you're doing. Obviously, if you turn your camera off again, that seemed to work, but it
mhm.
could just be that you just needed to drop your camera and the imagery be fine. We can just have your little avatar up for those last
Yeah.
few seconds. So thank you everyone for
Yeah.
watching.
And maybe
Um,
I'm on X. Yeah, maybe a short advertisement. My name is
please, yeah,
yeah, exactly. It's X at TechTranslate _G at X, former Twitter. And basically, this is basically also my. Do you see this? My avatar.
yeah, that actually works
And
quite well
basically
because your
on X. No?
sound is
And I
working.
have also the same background there. And when you go to my profile and you look at the highlights, you will find some of the slides which I showed today. No, and if you're interested, I would appreciate if you follow me and like some of my posts, because a lot of flat earther, they call me names because
They
they don't like
pick on him
reality.
over there.
Yeah.
No, this is the problem. This is like what I was saying before. Not going to call them stupid. Not going to call them dumb. It's not really what I do. You know, I might make fun and be a little bit sarcastic now and again, but I don't really kind of call them
Yeah.
stupid. Let's maybe it's Flatsoid because I'm pretty certain he's a bit stupid.
Yeah, this is really, as I told
Am I
you last
contradicting
week,
myself? Maybe a little bit, but
uh,
it's relevant.
normally
But yeah,
my
X
policy
is
is
a bit of a
also
cesspool, so
that I explain in a calm tone how it is. But last week I got such nonsense there. There I had to be sarcastic. It's normally I don't want this. I want to go back to being calm and just explaining, because I don't necessarily explain it to the one who think Earth is flat. But if somebody who is undecided read this, yeah, and maybe it brings him on the right path. This is basically my hope.
and your sarcasm is still funny. So you know they say the Germans don't have a sense of humor. I promise you, Tech has a great sense of humor,
Oh,
and
thank you.
and you should go on X and obviously support in there and subscribe. And while you're here, obviously subscribe to NOPEGENX. We do everything
Yep.
we can here. There's some entertainment with music. I generally do some form of reaction video at some point. We've got another one coming out soon, which will be on moon landing and some stuff that I've picked up off Facebook with basically people. Oh, you're still frozen.
Yeah.
Just some kind of general kind of almost like same mentioning Flatsoid. It's kind of like Flatsoid arguments, you know, like, oh, this happened. Isn't that a bit weird? This happened. Oh, that's a bit odd. You know, those kind of arguments that don't actually have any weight behind them. So I'm gonna dive into it basically. And they actually said and it's in the video. They actually wanted to look at it in detail. So it's turning into a bigger video than I expected. So I'll try and get it out for next week. But obviously, in the meantime, you've got nearly 3 hours of TechTranslate explaining Einstein's general
Oh,
relativity.
I look now on the watch. 2.5 hours. Am I right?
2 hours and 53 minutes
3
live
hours.
there, my friend. Yeah,
Jesus
you
Christ.
at it. Well,
Jesus
I don't
Christ.
think he was involved, but if he was, maybe he can condense it next
Yes,
time.
it's nearly 60 slides. I see 60
We
slides.
always
Oh my God.
me and Tech get together like obviously before we do any of these streams, and we always say that we're trying to aim for an hour next time. And, and
This
every
is
time we always say, let's
time
try and aim for an
dilation.
hour next time.
This is
Time
time dilation.
dilation, yeah.
This
This
time
is
dilation.
it. It's welcome to reality, everyone. Well,
This
thanks everyone for being here. Obviously, subscribe to both Tech on X, myself here. Check out our channels. Enjoy yourselves. Welcome to reality. You know, we'll put the ticker up. We'll put the ending up. Have a wonderful evening. And
okay.
as
Good
always,
night to
have a good one.
everyone, and thank you for listening. Yeah. Okay.
Welcome to reality.
So
1 second.
So I close this one. Ugh. I drank nearly a bottle of water here. Oh man.